Welcome back. Now we'll look at section 2.6.2, which is about rank. Rank and basis are closely related. Right? So let's see what this is. So the way that rank is defined is the number. So this pound symbol is used generally for the number. Okay. So the number of linearly independent columns of matrix A. Okay, matrix A which belongs to some R m by n. Okay, and this is how it is defined, and it also equals the number of linearly independent rows of A. Okay, and it's called the rank of A, right? And it's so that's rank of A and denoted by RK of A, right? So the number of linearly independent columns, and so there is another claim here, it equals the number of linearly independent rows. Okay, now this is same as what in the book is given in the remarks as the first remark, which is rank of A equals rank of A transpose. Okay. Or in other words, what they are calling as column rank. This is how many number of columns are linearly independent equals row rank. This is how many rows are linearly independent, right? There is no proof given for this, and intuitively the way to look at this is, if you take matrix A and then you look at especially the reduced row echelon form, right? So you know that wherever the pivot columns are there, you're going to have columns of the identity matrix, right? So, and then the non-pivot columns, you won't have they will have some other numbers. They are not going to be columns of the identity matrix, right? And then that way you can observe that the number of columns that are linearly independent will have ones in different columns, different rows, right? And then the same is true if you look at the rows also, because if you look from top to bottom, for example, let's take this, right? In this case, these pivot columns are going to remain even if we do this reduced row echelon form, right? Because this 1 and all zeros, and then 0 1 this, and then this is 0 0 1 and all this 0. These three columns will be columns of I5, right? This will be something else, right? But if you really look at it, the reduced row echelon form, these three columns are linearly independent. In the same way the rows also, right? Because really look at it, you can look at it vertically also, and it's going to be the same, right? So that is the intuition for column rank being same as the row rank. Okay, so this is the first remark in the book. Then the second remark in the book is the columns of A span a subspace U in Rm. Okay, so if you look at A is in Rm by n, so if you look at the columns are going to have m entries in them, right? So the columns of A span, so columns of A span a subspace U, and this U is a subspace of Rm, right? And width and dimension of U is going to be equal to rank of A, which is nothing but how many ever linearly independent columns are there in the A, right? The columns of A. Now, how do we find the basis for U? Basis for U we can easily form by just doing the reduced row echelon form. Just doing the dimensionality reduction and then basically Gaussian elimination, and then you identify the pivot columns, and then so this is Gaussian elimination and then taking the pivot columns, right? That will give us the basis for U. Okay. The next property is, the next one, now we look at the rows. The rows of A, again Rm by n, right? Rm by n, so that's going to span a subspace in some W, right? And this is going to be a subspace of Rn in this case, right? Because you have m rows and n columns, right? So if you just look at the rows, each row has n entries, n for Nancy, right? So n entries, span a subspace W in Rn, right? And then this dimension of W is going to be equal to, again, rank of A. Technically rank of A transpose, but that's same as rank of A. Again, you can find the basis using Gaussian elimination to, in this case, to A transpose. Okay, and then taking the pivot columns. Okay, the next point. So for all A in Rn by n, so square matrices. So A is regular or invertible, right? It's just regular is just another way to say invertible. If and only if rank of A equal to n. Okay. That's clear. Next we have so we take A in all A, actually for every A in Rm by n, and then B in Rm. Okay, so B is in Rm. Ax equal to B can be solved if and only if rank of A equals this augmented matrix rank of AB, right? Rank of equals, these two ranks are equal. Think about it. Obviously, if you want Ax equal to B to be solvable, then adding B should not be affecting the rank. Then only we can solve it. Okay, that's what this means. Then the next one, for A, now again we take Rm by n. So now we know that, let me write this. So the subspace of solutions of Ax equal to 0. So we know, before we already saw that if we take all the x's that solve this, right, then those x's form a subspace, because obviously the 0 vector is there, and then if you take any two solutions, then their sum also is a solution, and then if you scalar multiply an x that solves this, again that's also going to be a solution like lambda x, right? So closure property is satisfied when 0 is part of this. So that's why the solutions of this equation ax equal to 0 form a subspace. We saw this in the example before. So now we look at the same thing, but now we are interested in the dimension of this, right? Possesses dimension now. You think about it, ax equal to 0, and then this rank is there, rank of a, right? In the simple case, let's take, for example, let's say a is an n by n matrix and it's regular, right? Then the only x that can solve this is the 0 itself, right? Which means the solution, this solution space dimension is going to be 0, right? But otherwise, if a has some linearly dependent columns, then it's going to be n minus the rank of a, right? So n minus rank of a. If a is what is known as full rank, which means it has all n linearly independent columns, and I'm here taking n by n, then the dimension will be 0 for this solution space of ax equal to 0, right? So this subspace of solutions, this thing is called as a kernel or the null space of a, right? Kernel or null space of a, right? Then last one, again a is Rm by n, has full rank, is called full rank if its rank equals the largest possible rank for a matrix of the same dimensions. So what does this mean? So let's say m is less than n, then obviously the rank cannot be more than m. If m is, whichever is smaller, rank cannot be greater than that. So that's why they are writing like this, okay? Rank is going to be lesser of the number of rows and columns, right? So this is always true for full rank matrices. If the rank is not full, then this is less than or equal to, okay? So those are called rank deficient matrices, means rank of A is strictly less than the minimum of m comma n. That is rank deficient matrix, and then full rank matrices, okay? So we'll look at some examples next. So hopefully that will make this all notation a little bit more concrete. So this is these are examples given in example 2.18 on rank. So A equal to 1 0 0 0 1 0 and 1 1 0. So obviously this one we can see the bottom row is all zeros, and then we see that this 1 and 0 are there and they are flipped, which means you can't express this as any linear combination of this. So rank of A is 2, right? By looking at rows we can do that, or looking at columns we can see the third column is simply sum of the first two columns. So rank of A is 2, and then of course the second column cannot be expressed as any linear combination of just the first column alone, right? So that also matters. The next example given is you take a equal to 1, -2, 3, 2, -3, 5, 1, 1, 0. So we can do Gaussian elimination. Let's just go through the steps. So the first row you have 1, so this guy is R2, so we'll write R2 plus 2 times R1. R3 is going to be R3 minus 3 times R1, right? So then this becomes 1, 2, 1. This is going to be 0. So this is going to be 2 times this, so 4. So this will be 1. This will be 3. Okay. So minus 2 plus 2 is 0. Minus 3 plus 4 is 1. 1 plus 2 is 3. And then this 3 is there. So 3 minus 3 times this is 0. 5 minus 3 times this is -1. So this is -3. Let me check this. So 3 minus, then this is -1, -3. Now this is the pivot next. So we'll just do R3. So R3 plus R2. This becomes 1, 2, 1, 0, 1, 3. So you add them up, this becomes all zeros, right? So this and this are the pivots, right? So rank is 2, right? If you want to go one step further to do, so this is the REF. So let's just do RREF. So for that we are going to take R1, say R1 is R1 minus 2R2 to this guy, right? So that's to this guy. So we'll get, so this will be 1, multiply this times 2, so this becomes 0, multiply this times 2, 6, so this becomes -5, then this becomes 0, 1, 3, 0, 0, 0, right? So what we did here is we just basically wanted this guy to be 0, right? So we just multiplied this whole thing by times 2, subtracted it. What this tells us is basically this is minus 5 times this plus 3 times this. So what this is, again I'm just going back a little bit to linear dependence here and independence. So this what this is saying is minus 5 and 3, so we can verify, right? So now I'm just verifying. Is 1, 1, 0 is, that's x3, is this equal to -5 times the first column, 1, -2, 3, plus 3 times the second column, which is this 2, -3, 5. Right, so let's verify that. So this is -5 plus 6, so that's 1. Then this is 10 minus 9, so that's 1. Then this is this, so this works, right? So basically this third column is -5 times this column plus 3 times this column, so they are not linearly independent. And obviously, like you remember, we also discussed the rank of the, or the number of linearly independent columns same as number of linearly independent rows, which is clear from here because we can see that when you take the rows, it's obvious all 0 rows don't count, so this goes away. So rank is only just, and then this 1 and 0 you can't express as linear combination, so that's rank 2. And the same is true with the columns, which we just saw, right? So that's rank 2. So, but anyway, so this exercise was more for the rank of A being equal to 2. That's what this exercise, and the same thing for this matrix also, right? Usually with Gaussian elimination, we'll go all the way up, down, and then if we go up to reduced row echelon form, then we'll get all 0 rows, which is kind of, somewhat I feel is more convenient and easy to see. Yeah, I mean, more than the rows, it's in the columns. You can easily see that you can't express yeah, you can indeed express this as linear combination of the other two. So that's obvious. Okay, in reduced row echelon form. Okay, all right. So we'll stop this video here. We'll continue in the next one.